Discontinuity is one of the most important concepts in calculus. A function is continuous at a number a if the limit as x approaches a of the function is equal to f of a. Okay, what does that mean? Well, we're going to look at that definition in detail in just a moment, but let's have a practical, informal way that you can tell whether something is continuous or not. If you're looking for a practical test for continuity, a function is continuous wherever you can draw the graph without picking up your pen from the paper. So for instance, if we look at example number 1, if they asked me where is this continuous, well, it's continuous over here from negative infinity until I get to positive 1. At positive 1, I would have to pick up my pen to jump over that open dot. So there's going to be a discontinuity at positive 1. All right, then I would keep going, and when I get to positive 3, I've got to pick up my pen to jump up here because there's a gap in the graph. All right, then I would keep going, and when I get to positive 5, I've got to jump up here to fill in that open dot and then come back down to keep going. So I could say that this is not continuous at 1, at 3, and at 5. Now, if I'm going to say that something's not continuous, I have to give one of the 3 parts of the definition for continuity to explain that. So let's look at that formal definition of continuity. All right, we said up here that the function was continuous if the limit was equal to f of a. Okay, if the limit's going to equal f of a, doesn't f of a have to be defined? Like, I should be able to plug a into the function and get a numerical value. If the limit is going to equal f of a, wouldn't the limit have to exist? So I can't have a limit that's equal to a value if the limit does not exist. And then last, those 2 things, the limit and f of a, have to equal each other. So the answer that I found in number 1 needs to be equal to the answer that I found in number 2. Now you might remember that that is the same thing that we were calling well-behaved. When you could do direct substitution and plug your value into the function and the answer that you got was the same as your limit, then we said that that was well-behaved. So again, we have a 3-part formal definition that we're going to use in just a moment to test different values. We also have an informal definition where we can look at the graph and say, where did I have to pick up my pencil? Right here at positive 1 to jump over that dot. Right here at positive 3 to jump up to the other part of the graph. Right here at 5 because I have an open dot here that gets filled in up here. So let's look at then what would be the reasons for each of those discontinuities. It's got to be one of the 3 parts of this formal test or this formal definition. All right, so if we look at x is equal to 1, what's the problem there? What's the problem at 1? Well, the function is not defined. When x is equal to 1, what's your y value? There's a hole in the graph. It doesn't exist. So the problem at f of 1 is that the function is not defined there. All right, then let's come over here to positive 3. What's the problem at positive 3? Why is there a discontinuity here? Well, the limit from the left-hand side is approaching down here at perhaps -1. They didn't really give us a y scale. And the limit from the positive side, the limit from the right, is approaching a value up here, maybe, positive 3, something like that. So the limit from the left does not equal the limit from the right. All the values are not converging on one specific point. So therefore at 3, the limit does not exist. And the way that we can write that is we can say the limit as x approaches 3 from the left for the function does not equal the limit as x approaches 3 from the right of the function. All right, and then the last value, number 5, x is equal to 5, is the function defined? Well, yeah, right there. When x is equal to 5, there's a y value right there, so yes, it's defined. Second, does the limit exist? Well, the limit from the right and the limit from the left are all converging on one value. So yes, the limit does exist. But the problem here is that the answer that I got for f of a does not equal the answer that I got for the limit. And so that would be the problem. That's the third part of that definition, that the limit doesn't equal f of a. The answer that I got for number 1 and the answer that I got for number 2 are not the same thing. So they've given me an example of how all three parts of that definition can fail. That f of a has to be defined, the limit has to exist, and f of a has got to be equal to the limit. Now there are several different ways we can classify those discontinuities. First, a removable discontinuity is when I can just redefine that one point and it would resolve my discontinuity. A jump discontinuity is exactly what it sounds like. It has a jump in the graph. And an infinite discontinuity is one that's going to go to positive infinity or it's going to go to negative infinity. So if we go back and we look at these three discontinuities that we had for this first one, x equals 1, is that removable, jump, or infinite? Well, it's removable because if we just redefine that one point right there, then it would be continuous. All right, then if we come over here to 3, would that be removable, jump, or infinite? Well, there's definitely a jump in our graph here, a gap in our graph, so that would be a jump discontinuity. And then if we come over here to 5, removable, jump, or infinite, well, if you'll notice, if we redefine just this one point right here, then that would remove that discontinuity, and so that is a removable. And we'll see an example of an infinite in just a moment. All right, so frequently they will ask us to determine whether a function is continuous at a specific point. And the way that we'll do that is we'll use this formal test for continuity, this three-part definition that we were utilizing. All right, so to begin with, we want to know, is this rational function continuous at positive 1? So step number 1, I need to figure out, is the function defined? All right, so if it's defined, I should be able to put 1 into the function and get a value. All right, so if I plug 1 into that function in the place of x, I'm going to get negative 2 over negative 1 or positive 2. So yes, the function is defined. When I plugged in 1, I got a numerical value. All right, then second, I want to check and see, does the limit exist? Now, we know that this is a rational function, and we know that rational functions are well behaved within their domain. We know that a rational function is a polynomial divided by a polynomial, and that polynomials are well behaved. So we can do direct substitution here, and the answer that we get will be our limit as long as it's within the domain, as long as I don't get 0 in the denominator. So I've got a limit of 2. All right, so then the last thing that I need to check is, does the limit equal f of a? Did the answers that I got for 1 and 2, were they equal to each other? And so sure enough, f of 1 was equal to 2, and the limit was equal to 2. So I can just make a concise statement like this, that f of 1 is equal to 2 is equal to the limit. So since all three parts of the formal test worked, then I can say, yes, this is continuous at x is equal to 1. All right, let's go back and look at this exact same equation. This exact same function, only let's look at it for x is equal to 2. So again, I'm going to start with the first thing. I'm going to start with, is f of 2 defined? So the way that I check that is I literally plug 2 into the function. So if I plug 2 into the function, what happens? Well, I get 0 in the denominator. What is 0 in the denominator? It's undefined. So that very first part of the test fails. F of 2 is not defined. F of 2 is undefined. So if any one of those three parts of the test fail, then we know that our function is not continuous at that value. All right, let's look at another one. For this next one, they ask me if f of x is equal to 1 over x squared when x is not equal to 0, and 1 when x is equal to 0, is that function continuous at 0? All right, so again, we're going to use our three-part definition. So step number 1, we want to find out, is f of a defined? All right, so if we're looking to see is it continuous at 0, we're going to plug 0 into the function. So when I plug 0 into this piecewise defined function, am I going to use the top piece or the bottom piece? Well, it says if x is equal to 0, I'm supposed to use this piece, so I'm going to use the bottom piece. And it says when x is equal to 0, then f of x is equal to 1. Your y value is 1. So when x is equal to 0, my y value is 1. So yes, the function is defined at 0. All right, the next thing I want to look at is the limit. And so if I'm trying to take the limit as x approaches 0, am I going to use the top piece or am I going to use the bottom piece? Well, if you think about it, when you're taking the limit, you're looking for what is the y value doing as you are approaching the x value from the left and from the right. I don't care what's going on at the point. I only care about what's going on as I approach the point from the left and from the right. So I don't care what's going on at 0. I care what's going on at 0.1, 0.01, 0.001. All of those values are not equal to 0. So I'm going to use this top piece then for my limit. All right, so if I try, this is a rational function, and rational functions are well behaved within their domain, but if I try and do direct substitution, I get 0 in the denominator. That means that 0 is not in its domain. So we're going to need to approach this a different way, and this is like those logic problems that we had where we said our numerator is staying the same, and our denominator is getting smaller and smaller and smaller. If you think about it, as x is approaching 0, we'd be using values like 0.1, 0.01, and 0.001. So 0.1 squared, 0.01 squared, 0.001 squared. So my numerator is staying the same, and my denominator is getting smaller and smaller and smaller. So what's happening to my overall fraction? It's getting larger and larger and larger. So that limit would be infinity. If you thought about it from approaching 0 from the left-hand side as well, so that would be like negative 0.1 squared, negative 0.01 squared, negative 0.001 squared. Negative squared is positive. So again, my numerator is staying the same, my denominator is getting smaller and smaller, so my overall fraction is getting larger and larger. Now, can you have a limit of infinity? No, that means that your limit does not exist, and the reason that it does not exist is because it's going to infinity. So our second step is going to fail here, and because the second part of that test fails, then it cannot be continuous at 0. And our reasoning there would be because the limit at 0 does not exist. Now, this would be an example of an infinite discontinuity. Remember, we had the removable and the jump and the infinite. That would be an example of an infinite. All right, so let's look at another example. Here's another piecewise defined, and they're asking, is this piecewise defined continuous at x is equal to 2? All right, so step number 1, the first thing we're going to do is we're going to see if it's defined by plugging 2 into the function. All right, so when x is equal to 2, do I use the top piece of the piecewise or the bottom piece? Well, you can see right here, when x is equal to 2, I'm supposed to use this piece. So when x is equal to 2, then my y value is 1. All right, so the function is defined then. All right, so then step number 2, I want to find my limit. All right, so if I'm trying to find the limit as x approaches 2, am I going to use the top piece or am I going to use the bottom piece? Well, again, that same discussion we had a moment ago. We don't care what's going on at the point x equals 2. We care about what's going on as we approach the point from the left and from the right. And when we approach 2 from the left and from the right, like 1.9, 1.99, 1.999, 2.1, 2.01, 2.001, all of those values are not equal to 2. So we're going to use that top piece for our limit. Okay, so this is a rational function, and so to find the limit, I can use direct substitution. However, when I do direct substitution, when I plug that 2 in, I'm going to get 0 in the denominator. So does that mean the limit doesn't exist? No, it just means that I might need to do some factoring and canceling or something that will simplify it. So let's do that. Let's factor that numerator, and then we can cancel the x minus 2 in the numerator and the denominator, and that would leave us with just the limit of this polynomial. And again, polynomials are well behaved. We can use direct substitution. So when I plug in, I find out that there is a limit, that the limit does exist, and that it's 3. All right, so now for the third part of our test, the third part of our test says, does the limit equal f of a? So we want to find out, did the answer that we got for the first part equal the answer we got for the second part? Well, what was f of 2? It was 1. And what was the limit at 2? It was 3. So no, those aren't equal to each other, and so the third part of our definition fails, that f of a is not equal to the limit. And so we would say no, it's not continuous at 2 because f of a is not equal to the limit there. So they've given us a really great example here of, here's the 3-part definition of continuity and the test that we'll use. We've seen what that looks like on a graph, how each of those parts of the definition could fail, and we've also seen what it looks like algebraically. In this first one, all 3 parts of the test were true, so it was continuous. Here we saw what it looks like when f of a is not defined. Here we saw what it looks like when the limit doesn't exist, and here we saw what it looks like when the limit doesn't equal f of a. So we're going to take these exact same 3 equations. So this rational function right here, and this piecewise defined, and this piecewise defined, and we're going to look at those again. So occasionally, instead of asking me to evaluate continuity at a point, they'll give me the entire equation and ask me to tell where is it not continuous. So let's look at how can we tell where we even need to look. Okay, well, let's look at this first equation. The first thing I want to think about is, where is f of a defined? So if I'm looking for where a function is defined, the only thing I need to be worried about are domain issues. 0 in the denominator, negative under the square root of an even indexed radical. So when we're looking for where's the function defined, we can just think domain. So if I'm looking at this first rational function here, obviously I'm going to need to check x is equal to 2. There's going to be a problem there with the domain. All right, so sure enough, on that last example, they had asked us to check it at 2, and we did find out that it was not continuous there because it was not defined. All right, so let's look at the next example. For the next example, again, we worked on this one when they asked us to evaluate its continuity at a point, But again, we're trying to determine how would we identify where those problems would be if they gave us the whole function and said, where is this discontinuous? And they didn't tell me the specific points to check. So again, I'm going to start with where is the function not defined? I'm going to start with domain issues. So you can see right here that when x is equal to 0, this is going to be undefined. So 0 would be a domain issue, but you'll notice they've already addressed that. They've said use this if x is not equal to 0. If x is equal to 0, they have redefined the function in a different way to avoid that domain issue. So I don't have a problem there with the function not being defined, all right? Then second, I would want to consider the limit. All right, so when I'm thinking about the limit, again, I can see that when I've got the numerator staying the same and the denominator getting smaller and smaller where we're approaching 0, we know that we're going to have an infinite limit there. And so that would cause a problem for us. So we would say that that is at 0. Another place that you always want to check a piecewise defined function is where the pieces come together, because for the limit, even though the first piece may be continuous and the second piece may be continuous, if they don't come together, then your limit from the left would not equal your limit from the right. So we always want to check where the two pieces meet. So in each of those scenarios, the infinite limit or where the pieces meet, both of those, the issue was at 0, and so that would tell me that I would want to check 0. And of course, we just did that a moment ago, and we found out that the limit didn't exist and it wasn't continuous there for that reason. All right, then let's look at this last one. All right, so again, we've just worked this problem a moment ago. But if we have to look at this and identify the places where the limit doesn't exist, the first thing I'm going to do is look for domain issues. So when x is equal to 2, I would have undefined here. And so again, you'll notice it says, okay, we'll use this for when x is not equal to 2. When x is equal to 2, they have redefined the function elsewhere. So therefore, that's not a domain problem if they've redefined it. All right, then step number 2, we would want to determine the limit. All right, so we could take this and it's a rational function. We could go through and factor and cancel and see that we would be able to find the limit. And of course, the limit of a constant is that constant. So the other thing that we're going to need to watch out for, again, with a piecewise defined is where the pieces come together. And so I would want to check where those pieces come together, and that's how I could identify the two where I would find out that the limit did not equal f of 2. So again, we've got an example of each of the 3 parts of the test for continuity, and we've seen it with a graph, we've seen it at points, and we've seen it looking at equations as a whole.